Welcome back to this next video in which we are discussing splitting fields. Okay, so as promised in this next video, we're going to discuss the proof of the existence of a splitting field. Okay, so we're going to start off with a field capital F, and we're going to have some polynomial p of x that is in the ring of polynomials over that field capital F. And we now want to prove that there exists a splitting field for this polynomial p of x over the field capital F. Now remember, the polynomial p of x, we're assuming it's a non-zero polynomial and that it's a non-constant polynomial. Okay, right, so let's begin then. So to start with, what we're going to try and prove is something slightly easier, something slightly more general. We're going to start by just trying to prove that there exists a field extension of f such that p of x splits into degree 1 factors in the ring of polynomials over that field extension of f. Okay, we're going to neglect this second portion. We're just going to try and prove that there exists a field extension of f which obeys the first part of a splitting field first, and then we'll pay attention to this one here. Okay, right, so this isn't going to be a splitting field, this is just going to be a field extension of f. Okay, so we're trying to prove that there exists E, which is a field extension of f, and I'll just put, we're trying to prove that there exists E, which is a field extension of f. So rather than calling it k, because it's not going to be a splitting field, I'm going to call it E. So we want to prove there exists E, which is a field extension of f, such that p of x splits completely into degree 1 factors in the ring of polynomials over this field extension E. Okay, splits in the ring of polynomials over the field extension of f, which is E here. Okay, so that's what we're going to try and prove initially, and then we'll pay attention to the second part. We'll correct it so that the second part is going to be true as well. Okay, so firstly then, let's try and prove this. So how are we going to do this? Well, we're going to actually do this by proof by induction. Okay, so here we go, proof, and it's going to be by induction. So you might be asking, well, what are we going to actually induct on? Well, we're going to induct on the degree of the polynomial. So we're going to start off by proving that it's true if the polynomial p of x has degree 1, and then we're going to show that if it's true for degree 1, then it's true for degree 2, and if it's true for degree 2, it's true for degree 3, and if it's true for degree 3, it's true for degree 4, i.e. we're going to prove it by induction on the degree of the polynomial. Okay, right, so proof by induction then. So starting off then with the case where the degree of the polynomial is equal to 1. So we'll start with the degree of this polynomial p of x is equal to 1. Now, of course, if the degree of the polynomial is equal to 1, then this is very trivial, because the polynomial is already split down into its factorization in terms of degree 1 polynomials. So therefore I can just let my field E, the field extension of f, which this polynomial is going to split down into a factorization in terms of degree 1 polynomials in the ring of polynomials over that, I can just let it equal f, because of course in the ring of polynomials over f, p of x is writable in its degree 1 factorization. Okay, so clearly then, E exists in the case that the degree of the polynomial is equal to 1. Okay, so that's very trivial. Now what we're going to do is have the assumptive step. Okay, so here is the assumption step. So we're going to now assume that the theorem is true. So we're going to assume that it's true for the degree of the polynomial. So for degree of the polynomial p of x is less than, strictly less than n, where, and in fact actually, shall I use some different letter to n, because we're using n for the degree of the polynomial. I will use k, okay, and that should be a lowercase k, because obviously k is denoting our field extension, our splitting field. But yeah, this is just a lowercase k, and in fact actually let me come up with something different, okay, so that there's no confusion at all. We'll call it h. Okay, so we'll assume that it's true for the degree of the polynomial is strictly less than h, where h is some natural number. Okay, so it could be 13, 14, okay, and now what we're trying to show, so to show that it's now true for the degree of the polynomial is equal to h. Okay, so we want to show that the degree of the polynomial is equal to h, that it's true for this. Okay, so true missed out a few words, want to show that it's true for the degree of the polynomial p of x is equal to h. Okay, and if we can show that, then of course we've completed the proof by induction, because if this is true, then because it's true for 1, it'll be true for 2 by this, and then because it's true for 1 and 2, it'll be true for 3, and then because it's true for 1, 2 and 3, it'll be true for 4, etc. i.e. we will be able to prove it, we'll be able to claim that it's true by induction for all degrees of the polynomial that you can possibly come up with. Okay, right, so firstly, let me just make sure that everyone understands by what I mean by true. Okay, so my statement in this proof by induction then is that there exists a field extension of f, which we're calling E, such that the polynomial p of x splits in the ring of polynomials over that field extension of f, which we're calling E. Okay, splits into linear factors. So that's the statement that I'm trying to prove is true. So I'm assuming that for degree of the polynomial is strictly less than h then, that there does indeed exist a field extension of f such that the polynomial p of x will split in the ring of polynomials over that field extension. And I'm now trying to prove that if we have a polynomial of degree equal to h, that indeed there will exist a field extension of f such that the polynomial will split in that field extension. Okay, so how am I going to do this? Well, there are two cases here, so I'm going to split it down into two cases. So case 1 and then case 2. Now case 1 is extremely easy, case 2 is the more difficult one. Okay, so this polynomial p of x, it is an element of the ring of polynomials over the field capital F. Now of course the ring of polynomials over a field is always a unique factorization domain, so there is going to be a factorization of this polynomial p of x into a bunch of irreducible polynomials. Now case 1 is where when you factor this polynomial p of x into its irreducible polynomials in the ring of polynomials over the field, you get all degree 1 polynomials, i.e. case 1 is where this polynomial just happens to split already in the ring of polynomials over the field. Okay, so how should I write this? Irreducible factorization, or irreducible, how should I put this? Irreducible factorization yields all degree 1 polynomials. So irreducible factorization yields all degree 1 polynomials, i.e. f is indeed the splitting field for this polynomial p of x over f. Okay, all degree 1 polynomials. Okay, and this is why this is the easy case. In this case, we can just set our field extension of fe equal to f, and then of course this polynomial p of x will split in the ring of polynomials over f, because that's the statement here. We're assuming that its irreducible factorization in the ring of polynomials over the field f is a bunch of degree 1 polynomials multiplied together, and therefore of course that is it splitting into degree 1 polynomials. So that's case 1, that's the simple case where we can assume that this field E in which the polynomial is going to split is equal to f. Okay, now case 2. So case 2 is the less easy case. Case 2 is where there is at least one irreducible factor of p of x, where the degree of that irreducible factor is greater than or equal to 2. Okay, so in case 2, at least one irreducible factor, okay, so at least one irreducible factor of p of x in the ring of polynomials over the field capital F. So at least one irreducible factor of p of x has degree greater than or equal to 2. So those are the only two cases. Okay, so degree greater than or equal to 2. Okay, either the irreducible factorization is made up completely of degree 1 polynomials in the ring of polynomials over the field capital F, or in the irreducible factorization there has to exist at least one polynomial factor which is irreducible of degree greater than or equal to 2. Now let's give this factor, this irreducible factor of degree greater than or equal to 2, a name. Okay, so I'm going to give it a name. We will call it P1. Oh, actually, no, what do I want to call this? I'll call this f1 of x here. Okay, so call it f1 of x. Okay, right, so I'm saying that when I factorize p of x in the ring of polynomials over the field capital F, one of the irreducible factors that I get is this f1 of x, and this has degree greater than or equal to 2. So f1 of x here is some polynomial in the ring of polynomials over the field capital F. Now, here comes the great argument, okay? But by the way, I've proven it for case 2. We know that I've proven it for case 1. If case 1 is true, then we have found E, so we've proven that E exists. Now what we need to do is focus on case 2, so now we're just going to focus on case 2. So, the question now is, how are we going to show that E exists in this case? Well, of course, there's a natural thing to do. We've found this polynomial, f1 of x, which is irreducible in the ring of polynomials over the field capital F. Okay, it's of degree greater than or equal to 2. This is one of the ideal things that we discussed in the video on field extensions, which we can use to generate a principal ideal of, which we can quotient the ring of polynomials over the field out by. Okay, so what I'm now going to construct is what I'll call E1 here. So I'm going to construct something called E1, which is going to be the field extension of F constructed by taking the ring of polynomials over the field capital F and quotienting it out by the principal ideal generated by this polynomial f1 of x, which is this irreducible factor of p of x that is of degree 2 or greater. Okay, so I can construct this thing, and I hope that your knowledge of field extensions from the video on field extensions earlier on in this playlist on field theory is good enough that you appreciate that E1 is going to be a field extension of capital F. Whenever you do this, you end up with a field extension of capital F. There's a very natural way of including F into this. So we construct this field extension of capital F, which I'm calling E1 here. And now what's the great thing about E1? The great thing about E1 is that not only is it going to contain F, but it's also going to contain a root to this polynomial f1 of x, which previously was irreducible in the ring of polynomials over the field capital F. Okay, so whenever you indeed do this, you will add in a root to this irreducible polynomial which you use to produce the principal ideal which you quotiented out by. Okay, that's one of usually the reasons for doing this. And of course this polynomial won't have had a root in the original field capital F, otherwise it wouldn't have been irreducible in the ring of polynomials over the field capital F. You'd have been able to factor out that linear factor x minus the root. Okay, right, so we're now going to give the root a name. Okay, so let's say alpha 1 is an element of our field extension E1, and alpha 1 is the root for this polynomial f1 of x. So when I evaluate f1 at alpha 1, I'm going to get 0 in the field extension E. Okay, so alpha 1 is the root of the polynomial f1 of x in the field extension E1 of f. Now, why is this so brilliant? Well, now let's think about working in this field extension E1 of f. In this field extension, the original polynomial p of x still makes sense. Okay, so p of x is certainly still an element of the ring of polynomials over this field extension E1 of f. Okay? Because this is just a field extension of f, so a polynomial that was originally in the ring of polynomials over the field capital F is certainly still a polynomial in the ring of polynomials over a field extension of f. Okay, and now the great thing about this is that alpha 1 is going to be a root of this, because p of x, you know, has as a factor f1 of x. That's still true in here. You can still write p of x as f1 of x times something else. But now, of course, if f1 has alpha 1 as a root, then that means that p of x, which is a multiple of f1 of x, is also going to have alpha 1 as a root. Okay, so we can conclude that p of alpha 1 is equal to 0, and what that means is that I can now write p of x as the linear factor x minus alpha 1 times some other polynomial, the quotient of this. Okay, and I'll call that other polynomial p1 of x, and I apologise for, you know, having so much awkward notation. We've got e1, f1, p1 here, okay, but this really is the only way to do this. Okay, so p of x can be written then as this degree 1 factor times p1 of x when we're talking now about the ring of polynomials over the field extension E1, because of course alpha 1 is only a root of E1, it's not, is only an element of E1, it's not in F. So this polynomial here, where we've got x plus the additive inverse of alpha 1, that's not an element of the ring of polynomials over the original field F. So this statement is only applicable in the ring of polynomials over the field extension E1. Okay, now where can we go from this? Well, the key thing to note here is what's the degree of this polynomial? The degree of this polynomial is n minus 1. Degree h minus 1, we'll say, okay, because we're assuming that the degree of the polynomial originally to start with was h, okay, we changed notation, I was about to put n minus 1 there, but it's degree h minus 1, so we started with the polynomial p of x, that was of degree h, and now we've written it as x minus alpha 1 times this other polynomial, and that other polynomial now must have degree h minus 1. Okay, right, so what we can now do is apply the assumption that we made, because we assumed that it was true that if you had a polynomial of degree less than h, no matter what field you're working in, you could always construct a field extension of it such that that polynomial splits in that ring of polynomials over that field extension. So now we've got this polynomial p1 of x here, which is an element of the ring of polynomials over the field E1, okay? And now we can say, okay, this polynomial is of degree h minus 1, okay? It's from this ring of polynomials over this field. Construct me a field extension of E1, which is going to be a not a splitting field, it's going to be a field in which this polynomial p1 of x is going to split. Okay, so we're now going to construct E, which will be a field extension of E1, such that this polynomial p1 of x splits in E. Okay, so it will split into linear factors in E. Okay, right, so there is how we've applied the assumptive step now. So we now have this largest field E, and the reason I've called it E is because my next line is going to be, okay, use this as your field extension of the original field F, which is going to be the field in which your polynomial p of x will split. Okay? Right, so that's why I've called it E. But we can always do this applying the assumptive step, because E1 after all is just a field. It's got as much right to be used as a field as the initial field capital F. Okay, and we assume that if we had a polynomial that was of degree less than h in a ring of polynomials over a field, that you could always construct a larger field, a field extension of that field, such that the polynomial will split in the ring of polynomials. That should be the ring of polynomials with coefficients in the field capital E here. Okay, right, so that is always doable. And now, of course, the claim is, now view this largest field that we've created here, this E, as a field extension of F. Okay, we created it as a field extension of E1, but E1 itself is a field extension of F. So if this thing is a field extension of E1 and E1 is a field extension of F, then of course E is a field extension of F. Okay, so now view E as a field extension of F, and consider the polynomial p of x, okay, in the ring of polynomials over this field E. Okay, then my claim is that this is going to split down now into degree 1 factors, into a product of degree 1 factors in this ring of polynomials over this field capital E. Okay, now why is that going to be true? Well, because the polynomial x plus the additive inverse of alpha 1 is certainly going to be an element of the ring of polynomials over this field E, because this was a field extension of E1 and this was a polynomial in the ring of polynomials over the field E1. Okay, and now we know that this polynomial p1 of x, this splits into degree 1 factors in the ring of polynomials over the field E. Okay, so therefore my polynomial p of x is going to now be writable as a string of degree 1 factors in the ring of polynomials over the field capital E. Okay, so there you go. I have now, through induction, proven that there must exist a field E for which the polynomial p of x is going to split in the ring of polynomials over that field. Okay, right. And I should just say, we've started that it was true. We started with the assumption, the statement that it was true for polynomials of degree 1. Okay. From what we've now proven, you can conclude that it's going to be true for polynomials of degree 2, and then you can conclude that because it will be true for polynomials of degree 1 and 2, it will be true for polynomials of degree 3, and then because it's true for polynomials of degree 1, 2, and 3, it'll be true for polynomials of degree 4, and then etc. Okay, so it's the standard way that a proof by induction usually works. Okay, so what we've overall now proven is that if you have a polynomial p of x, which is an element of the ring of polynomials over the field capital F, then it is always possible to construct a field capital E, which is a field extension of capital F, such that the polynomial p of x splits completely into degree 1 factors in the ring of polynomials over that field extension E of F. Okay, the question now becomes, how can we use this to prove the existence of a splitting field? Because this isn't yet a splitting field. This is just a field in which the polynomial splits. Remember, a splitting field must be the smallest field extension of f in which the polynomial p of x splits. Okay, well what we can do is use this to, of course, construct a splitting field. Now how can we do this? Well, the instant we have some field extension of f in which the polynomial splits, then it is always possible to now write the polynomial as a string of degree 1 factors. So in this field E, we can write the polynomial p of x as a factorization in terms of its degree 1 factors. Okay, so let's start by doing that, and we'll do it in the clever way that I did before. Okay, so we'll have now ph, because we've updated the notation here, times x minus alpha 1 to the power of n1. Okay, so ph is going to be the leading coefficient of our degree h polynomial p of x. Okay, then we've got the x minus alpha 1, where alpha 1 is a root and n1 is the multiplicity of that root. Then we'll have x minus alpha 2 times n2, and that will go all the way up to x minus alpha k to the power of nk here. Okay, so once we've got a field in which the polynomial splits, you can write it in this standard form here, where you now have all of the roots appearing in a degree 1 polynomial like so, with the multiplicity of the root being the power that you need to raise that degree 1 factor corresponding to that root 2 in this factorization here. Now what we can do is we can say, okay, consider all of the subfields of capital E here which completely contain f, okay, so they're all field extensions of f, and which also contain all of these roots, so alpha 1, alpha 2, all the way up to alpha k. Okay, so you're going to consider all of the, let's say, fields L, which are in between E and F. Okay, so they have to completely contain F, and themselves they need to be completely contained in E. So you look at all subfields of E, which are field extensions of F, okay, and you're looking for them to all contain all of these roots. So you want them to contain alpha 1, alpha 2, all the way up to alpha k here. So you look at all fields that are in between these two and which satisfy this condition that they contain all of the roots, alpha 1, alpha 2, all the way up to alpha k. Okay, you take all such subfields of E which obey that criterion, these two criteria here, and then you intersect them all together. So we'll intersect all of these, Li, where I is some element of an index set here. Okay, so you intersect all such subfields of E which contain all the roots then of the polynomial p of x together, and I claim that this is going to be our splitting field. Now the first thing to say is that this will still be a field in which the polynomial will split in the ring of polynomials over that field, and the reason is that it will contain all of the roots alpha 1, alpha 2, all the way up to alpha k, because all of these Li's contain alpha 1, alpha 2, all the way up to alpha k, and therefore the ring of polynomials over this field capital K will contain all of these polynomials that we need to write the polynomial in its degree 1 factorization. In addition, this of course will be a field when you intersect all of these field extensions of f together. We know from the video on intersection of field extensions that when you intersect those of field extensions together, you end up with another field extension. So this still will be a field extension of f that contains all of these roots. Okay, so it's looking good. Now, why can we claim that it is the smallest such field extension? Okay, so why can we claim that there cannot exist a proper subfield of this in which the polynomial p of x splits into degree 1 polynomials? Well, of course, the reason is that any subfield of this in which the polynomial p of x splits into degree 1 polynomials is also going to be a subfield of E, which will contain all of the roots. So it will have been one of the things that we intersected together. Okay, and that would contradict it being properly contained within K, because K would contain, well, K would be contained within it. Okay, so that's how we can argue that indeed this is going to be the splitting field. So now I have proven to you that you can always construct a splitting field. Okay, so we'll call it there for this video, and in the next video what we'll do is prove the uniqueness of a splitting field.